Hello everyone, I'm Professor Harrison and welcome back to our module on matrix algebra for finance. Today we're covering row operations and row echelon form. These are the basic moves that we're going to take an augmented matrix and manipulate it into a form where the solution to a linear system of equations can be read right off the page. We're following Ruth, a PhD student building out her matrix-based methodology for her dissertation. Today she's not working on her own chapter though. Her friend and co-PhD student Victor has fallen behind on his asset pricing dissertation, and he's been bringing problems to Ruth for weeks to help him catch up. Today's problem is a multi-asset portfolio replication that Victor needs to solve for the chapter that he's drafting. Ruth happily agrees to help him through his work and walks up to the chalkboard to get started. So back in video 52, we saw how a linear system of equations can be written in matrix form as AX equals B, and we packaged everything we need into a single object called an augmented matrix, A with a line B. That gave us the setup, but what we haven't covered yet is how to actually solve it. How to take that augmented matrix and get the numbers out on the other end. That's what we're going to do today. The tools end up being three simple operations on the rows of an augmented matrix, and the target we're aiming for is a clean staircase pattern called row echelon form. Once we get the matrix into that form, the rest is mostly mechanical. Before we get into the operations, let's set up the problem Victor brought over. He needs to replicate a target factor exposure profile using three assets. Each asset has its own exposure to size, value, and momentum, and Victor needs to know how many of each unit of asset he needs to hold so that the combined portfolio matches the target exactly. The asset exposures in the target give us the system. 0 times the weight in asset A plus 1 times the weight on asset B plus 2 times the weight on asset C must equal 5. 1 times the weight in asset A plus 2 times the weight in asset B plus 1 times the weight in asset C must equal 6, and 2 times the weight on asset A plus 1 times the weight on asset B plus 3 times the weight on asset C must equal 11. We can write this as the augmented matrix as follows. So we have three equations, three unknowns, all packaged into one single object. So what exactly is this augmented matrix actually telling us? Well, each of the columns in this matrix, besides the last one, gives us how each of our three assets is exposed to each of the factors. So, for example, if we invest only in asset A and nothing into the other two assets, then we would end up with a portfolio that had 0 exposure to the size factor, an exposure of 1 to the value factor, and an exposure of 2 to the momentum factor. You can see that we could put a whole bunch of different weights into each of these three assets, and in doing so, we're going to end up with different exposures. Ultimately, we want to create a system that has our exposure equal to the values on the right side of the vertical bar. So for example, some combination we want to find of these three assets will give us an exposure of 5 to the size premium, 6 to the value premium, and 11 to the momentum premium. But how exactly do we actually manipulate this to figure out what weight we should put into each of these assets? To figure things out, we're going to work with three elementary row operations. The three operations that we are allowed to perform on the rows of an augmented matrix are called the following. The first is the row swap. This means that we're allowed to swap any two rows of the matrix if it makes solving the matrix easier for us. The second is row scaling. We're allowed to multiply any row by a non-zero scalar. And the third is row replacement. We can replace any row by itself plus a scalar of another row. So where do these three operations come from? The idea is that each of them preserves the solution set of the underlying system. So swapping two rows just changes the order that we've listed the equations in. Scaling a row by a non-zero number is the same as multiplying both sides of one equation by a non-zero number, which is why in any algebra class, you'll learn that that's completely fine. Then a row replacement is the matrix version of adding a multiple of one equation to another to eliminate a variable. Now this may sound complicated, but it's actually something you probably did back when you were in middle school. Do you remember back in the day when you had two systems of equations, and all you had to do was just add them down together in order to cancel things out, and give it so that you had the solution to the system? That's something that you did way back in the day, and really what you were doing was matrix algebra, and you probably didn't even realize. So the idea behind this process is that any two augmented matrices that you can get from one another using only these three operations will describe exactly the same system and will arrive to the exact same solution. We're going to call those two different types of matrices that explain the same thing row equivalent. That property is how this whole procedure works. We can transform the matrix as much as we'd like without changing the correct answer. So what are we going to do with these three operations? The idea is that we're trying to create the augmented matrix that is in a specific clean shape called row echelon form, or REF for short. Row echelon form has two requirements. First, the leading entry of each row, which is the first non-zero number from the left in that row, has to be further to the right than the leading entry of the row above it. So the leading entries form a staircase that steps down to the right as you go down the matrix diagonal. And second, in any column that contains a leading entry, every entry below that leading entry has to be zero. The leading entries themselves get a special name, and we're going to call them pivots. And we'll see in a second why this helps us actually solve the equations. So let's apply this to the row operations of Victor's system in order to get a row echelon form matrix. The first thing we want to do is have a clean pivot in the top left corner. So right now, the entry in the top left is 0, and 0 cannot be a pivot, because pivots are leading non-zero entries by definition. So what we can do is run a row swap. We swap row 1 and row 2, which gives us 1216, 0125, and 21311. All we've done is change the order of our equations, which is perfectly valid and doesn't change the information that the equations contain. Now row 1 has a leading 1 in the top left. That is our first pivot. The entry directly below it in row 2 is already 0, which is great. But the entry in row 3, column 1 is a 2, and we need it to be 0. So how are we going to cancel it out? What we need to do is a row replacement, and the reason why we'll do this will become apparent in just a second. The idea is that we want that bottom left entry to be 0. So to get it there, what we can do is subtract off row 1 times 2, which will make it so that our last row has a leading 0. Let's see how that works out. 2 times row 1 is 2, 4, 2, 12. So subtracting that from row 3 gives us 0, -3, 1, -1. So why exactly can we do this? Well, if you think about it, you're always allowed to add the same thing to both sides of an equation. That's also true if you take one piece of another equation, which is equal to the other side of it, and add it to both sides of your equation. So for example, what we did here is we took our equation in row 3 and we subtracted off 2 times each side of the equation in row 1. Because we're just adding the same thing which is equivalent to both sides of the equation, this is a perfectly valid thing to do in algebra. And the good news is now we've completed our first column. The pivot is in place and everything below it is 0. And now what we have to do is move on to the second column. The leading entry of row 2 is a 1 in column 2. That is our second pivot. The problem is that we need the entry directly below it to also be 0, but right now it's -3. So we do another row replacement. We replace row 3 with row 3 plus 3 times row 2. 3 times row 2 is 0, 3, 6, 15. Adding that to row 3 gives us 0, 0, 7, and 14. So now the first two columns are clean. There's a leading 7 in row 3, column 3, with zeros to the left, and that is already a valid row echelon form. The staircase steps down the right, and there is nothing below the bottom pivot to clear. But it ends up being conventional to scale the bottom pivot to a 1 so that everything is a little bit easier to solve downstream. So we do one row scaling. We multiply row 3 by 1/7, which turns out to 0, 0, 1, 2. So now we have our row echelon form. The pivots are the ones sitting in the diagonal, with 3 pivots in a 3x3 matrix. The staircase steps down and to the right, and every entry below each pivot is 0. So why exactly did we solve for this form? Well, now what we can actually do is start reading off part of the solution. Think about what this augmented matrix actually represents. Each one of these rows is just an equation. It gives us coefficients that go in front of each of the weights in our portfolio. So for example, what does our last row say? It says 0 times our weight in asset A plus 0 times our weight in asset B plus 1 times our weight in asset C equals 2. So what does that mean? Well, it tells us that our weight in asset C must be 2. So in row 3, we've effectively solved for one of the weights in our portfolio. We know that our weight in asset C has to be 2. And now what we can do is actually use that to solve for the rest of the weights. Let's move up to the middle row. It reads 0, 1, 2, 5. So as an equation, the middle row says that the weight on asset B plus 2 times the weight on asset C equals 5. And we already know that the weight on asset C is 2. So we plug it in. The weight on asset B plus 2 times 2 equals 5. So we know that the weight on asset B plus 4 equals 5, so the weight on asset B must equal 1. Now we move up to the top row. It reads 1, 2, 1, 6. So as an equation, the top row says that the weight on asset A plus 2 times the weight on asset B plus 1 times the weight on asset C equals 6. We already know both of the other weights. So the weight on asset B alone is 1, and the weight on asset C is 2. Plugging those in gives us the weight on asset A. Plus 2 plus 2 equals 6. So the weight on asset A must equal 2. Now we have our full solution. We need to buy 2 units of asset A, 1 unit of asset B, and 2 units of asset C. This technique has a name. It's called back substitution, because you start from the back of the matrix at the bottom row and you substitute the values you find as you work your way up. The staircase structure of row echelon form is exactly what makes back substitution work. Each row from the bottom up has 1 fewer unknown than the row above it. So each row gives you exactly 1 new variable as you go. So we end up with a complete procedure for solving the system. The 3 row operations get the augmented matrix into row echelon form, and back substitution reads the solution off the rows. Ruth steps back from the chalkboard. Victor finishes copying the steps into his notes. He has followed the procedure cleanly, and the portfolio system he came in with is now in a form that he can actually use. He's 1 step further along in his own chapter that he needs to write to get his dissertation completed. Row operations end up being the procedural engine of everything that Ruth is going to do in her chapters too. So that's row operations, row echelon form, and back substitution. 3 operations, row swap, row scaling, and row replacement, are the way that we solve for row echelon form. We have 1 target form, which is the staircase of pivots, with zeros below each one. The key fact that makes any of this work is that the 3 operations preserve the solution set of the system. So row equivalent augmented matrices describe the same problem. And once we're in a row echelon form, back substitution reads off the values from the bottom up to give us the solution.